Hello everyone, welcome to my channel. Today we will learn how to interface stepper motor with LabVIEW using NI-USB 6008 data acquisition card. Before going for interfacing the stepper motor, we should have basic knowledge about how a stepper motor works. To know about it, I recommend to watch this video. This guy has beautifully explained it. Let's see some of the features of the stepper motor. We know that a stepper motor is used where low speed and high torque is required. For high speed requirement, use servo motor. Stepper motor rotates in step, not continuously, and used for open loop position control where no feedback is used to tell about the position. Hence, we have to calibrate the position in terms of steps or angle. Then we have to give command to the rotor for that particular angle or steps to reach out the required position. Since it do not have any feedback system, it is less accurate than servo motor. Here I will be using the hybrid stepper motor, which has 4 starter coils and a total of 200 steps of size 1.8 degrees. Right. So these are the 4 coils named as A, B, C and D. Right. So but the rotor teeth is much more than what is shown over here. So the teeth almost up to 200, right? So for example, I have shown you this diagram. Practically the rotor have more teeth than this diagram, right? So I will drive the motor in full step mode. To rotate the stepper motor in full step mode, we have to give DC signal to the coils one at a time. First we have to give the signal coil A, then coil B, then coil C and coil D. We will not connect the DC signal, high signal, to any of the coils continuously, right? Or we cannot give the signal to all the coils at the same time, right? We have to change the signal sequentially from A to D, right? Hence I have to connect the 4 coils of stepper motor to 4 digital output ports of data acquisition card and generate digital high signal through each port sequentially, right? So let's see, these are the ports in the x-axis. So these are digital ports of the USB 6008 data acquisition card. These are the line 1, line 0, line 1, line 2 and line 3. And in the y-axis, these are the time frames. All the time frames have equal magnitude. Let's see, it is 200 milliseconds, right? So we will connect the port 0.0 to coil A, 0.1 to coil B, 0.2 to coil C and 0.3 to coil D, right? And then we will generate digital signals through each line sequentially. First we will generate the digital line in P0.0 for 200 milliseconds. Then we will generate the digital high signal in line 0.1 for 200 milliseconds. Then we will generate digital high signal in P0.2 for 200 milliseconds, and finally we will generate digital high signal in P0.3 for 200 milliseconds. Then we will repeat this pattern, right, to rotate the stepper motor. Right? And the time frame, the switching time decides the speed of the stepper motor. If we give less time between the switching of the signals between the coils, our stepper motor will rotate faster, and if you give more times, it will rotate slower, right? So that was the principle how we can rotate the stepper motor in full step mode. Let's see what are the components we need to interface with LabVIEW. First, we will need a driver IC, right? So this is ULN2003, or you can use ULN2803 IC. Okay. This is a Darlington pairs current amplifiers, right? It has 7 inputs and 7 outputs. So the inputs will be connected to data extraction side, and the outputs will be connected to the stepper motor side, right? The hybrid stepper motor requires more current and voltage, so that we will use external source, right? And this driver IC senses low digital signal from the data extraction card and gives high digital signal of 12 volt to the data extraction to the stepper motor to rotate, right? We need a breadboard to connect the stepper motor, data extraction card, and the driver IC together, and we will need, of course, some jumper cables, right? So let's see the connection diagram of the stepper motor, driver, and the data extraction card with the power supply. So this is the connection diagram, right? So these are the digital lines of the data extraction card. Okay, so this is P0.0, 0.1, 0.2, and 0.3, and this is the ground pin. And we will connect the output of this digital line to the input side of the data of the driver, and the corresponding pin at the output side will be connected to the stepper motor. First, we have to connect P0.0 to coil A through this IC, right? Then 0.1 to coil B, 0.2 to coil C, and 0.3 to coil D, right? And this is the external source to give the power to the stepper motor, and the common pin of the stepper motor will be connected to the common pin of the driver and the positive supply of the external source. And make sure the ground pin of the data extraction card and the external source must be connected in order to avoid the voltage difference, and the both will be connected at the ground pin of the driver chip, right? So this is the connection diagram what we will do in the breadboard. So let's connect it in the breadboard. So I have made all the connection, the stepper motor with driver IC and the data extraction card. So let's jump onto the PC and configure the data extraction card and make some LabVIEW code. So I am in my PC. The LabVIEW 2017 is open. So create a new file, that new VI. Okay, so we will configure the data extraction card to generate the sequential digital high signal to rotate the stepper motor. So for that we have to right click in the block diagram, go to Express, take input and DAC assistant, then click on generate signal, and we are going to generate digital output signal, and it is in line output. Our DAC assistant is detected over USB, so and we have to generate a digital signal through port 0.0, 0.1, 0.2 and 0.3. Let's select it, right, and click on finish, and then click on OK. Now the LabVIEW will build the VI of DAC assistant for us. Right. So to generate digital high signal sequentially from port P0.0 through P0.3, we will use a sequence structure called flat sequence. So where you can get it, right click on the block diagram, go to structure and click on the flat sequence. Right. So drag it, make a sequence, okay, and we will add 4 frames, right, so to generate 4 digital signals through 4 data acquisition lines. And these are the 4 frames. We have to resize it so that our DAC assistant will sit inside it, right. So put your DAC assistant inside the frame. So the LabVIEW starts executing the code from leftmost frame through the rightmost frame sequentially, right. So in the first frame we will make the port P0.0 high and all other ports to low, and in second frame we will make port P0.1 high and all other ports low, and so on. So how we can do that? We will create a constant, and it will create a constant of digital signals, right. We will expand it, so we need 4 signals, that's why we expanded to 4 signals, right. So this is the digital high and low constant array, and we will generate digital high signal for P0.0. That's why we will click on high or true on the first data of the array, right. Then we will make a copy of that in each frame, right, and we will change the signal in each frame, right. So this is P0.0, this is P0.1, this is P0.2, and this is P0.3, right. So we are generating the 4 signals sequentially through the attraction card, right. Now we have to put the wait millisecond block in each frame, so that the LabVIEW will wait at least that much of millisecond, right. Inside the frame. So create a constant, so we have to give 200 milliseconds for each frame, so that our digital high signal will be for 200 milliseconds, right. Then it will goes off and other port signal will be turned high, right. if the wait millisecond time is less, the sequence will be changed at faster speed that results in speeding up the motor rotation, right? And if the wait millisecond time is more, the motor will rotate at slower speed. Okay? And this, if you run this LabVIEW, this will run only once because there is no loop, right? And to rotate this stepper motor continuously, we have to put it inside a while loop. And create the stop button. Resize the stop button at the front panel so that we can stop the while loop by clicking it. Let's run the VI and see the result. So you can see the stepper motor is rotating, and I have connected 4 LEDs at the output of the driver so that you can see the execution of the sequence. Right? The LEDs are glowing sequentially. So let's stop the VI and change the delay, and you can see the effect of delay in the stepper motor speed. So if I make it 100, and rerun the VI, you can see the motor is rotating faster than the previous, right? So to rotate the stepper motor in clockwise or anti-clockwise direction, we will use a case structure with a direction control switch. Right. So in one case we will put our original code, and in the other case we will reverse the order of the sequence by changing the data control. Right. So let's stop it and do that. So we will take a case structure, and take a control digital, so in the first case we will change the data pattern, right? So that means first we will generate the digital high signal of P0.3 instead of P0.1, then P0.2, then P0.1, and finally we will generate the signal in P0.0. Just we change the pattern in the first section and in the true. So this will be in clockwise, and this signal will drive the motor in anti-clockwise direction, right? So let's run the VI and change the control so that you can see the direction of the motor. So let's run it. You can see our motor is running in the anti-clockwise direction right now. Now if I change the switch, it will run in clockwise direction. Right? So in this way we can change the direction of the rotation of the motor by toggling the switch from the front panel. Right? So this is the basic way to rotate a stepper motor by using LabVIEW and Daggett. What is the drawback of this method? To rotate the motor continuously irrespective of angle and step, this method is fine. But stepper motor is rarely used for continuously running. They are used to run for a specific angle or step. This basic method will fail to precisely control the angle. It's because in one iteration of the while loop, there are 4 sequences which will get executed, and one sequence drives the motor by one step, which is 1.8 degree. Since we cannot stop the while loop in halfway of the sequence by the stop button, in one iteration of the motor, the motor will cover 1.8 degree into 4, that is 7.2 degree. So we will see the second method where we could be able to control the angle precisely. So let's stop the VI and we will see the efficient method. So I have already made this code. Let's understand how it is working. As we know, to rotate stepper motor, we have to generate digital high signal through 4 ports, one after another. So we should have 4 cases, and in each case we have to generate digital high signal for a particular port. That's why I have used a case structure with 4 cases, and in each case my data pattern is different, just like the data pattern was for each frame in the sequence structure. Here in this technique, the motor will move only one step per iteration of the while loop, and we can stop the loop at any particular case so as to stop the motor at any particular angle or position. But the challenge is how to give the 4 inputs for the case, and the cases must repeat after 4 iterations. So I've used simple logic, that is, when any number is divided by 4, its remainder will fall between 0 and 3. I am dividing number from 1 to 4 by 4 and using the remainder as the case of the case, and incrementing the remainder after every iteration. So the last case value will be stored in the shift register. So I have used here the shift register, and it will save the last reminder value. Then in the next iteration it will increment it by 1, and then it will divide it by 4, and the remainder will be between 0 to 3, right? And it will be repeated by the while loop iteration after 4 iterations, right? So let's run this code and see how our stepper motor is reacting to this code. First, we have to configure the data action card. And it is 0. All the things are configured. So let's OK. Let's OK. So delete it and reconfigure it. Right? Then run the code and see the result. As you can see, as for our code, the stepper motor is running, right? And if you press the stop button at any instance, the motor will come to rest instantaneously. Right? So in this way, we can interface a stepper motor with LabVIEW using data acquisition card in a USB 6008. And we can use another case structure for the directional control of the stepper motor with efficient layers. Good. So thanks for listening. So thanks for watching.